Okay, now I have been emphasizing on averaging and Laplace equation. It's time to sort of give some kind of proof for especially for 3 dimensions. So the claim, let me make the claim first. Okay, the claim is that suppose I think of an what V average. Let me first state it. Okay, V average over a sphere of radius r is equal to r in a region which obeys Laplace equation. Okay, meaning it's charge free. So this, okay, is V average. You can think of to take a point and then take a sphere around it. Okay, this at this point Laplace equation or this region follows Laplace equation. So take this point and take a sphere of radius r. Let's say this is position r. Okay, then and it's free of charge because it obeys Laplace equation. But suppose I know the v is not constant, but it is varying over this surface. Now V average on this surface is, I'll define it as some VdA over the surface, over that sphere, over the sphere, and divided by the total area, 4 pi r square. So that is V average. So the claim is that V average around this surface is the same as the potential at the center of this point. So which means the claim is that V of r is this V average. V average, okay, is equal to r. And what is it? Just now the way I have said it is 1 by 4r square, the integral over V dA, and this is for r is equal to r sphere. So this is the claim. And you can realize, you can understand that this claim also is intimately related with the implication that the potential can have no maxima or minima. This is understandable because if there was a maxima or minima, then I couldn't be doing this averaging. Okay, only if it is monotonic. Otherwise, I can always choose that area which avoids that maxima. Okay, and then the average will not come out. Correct. So these two claims are actually related. Okay, so let's give a simple proof. Okay, proof assuming that it obeys Coulomb's law, which you know. So what we do is let's choose a point R, and then let's look at the effect on it of a Q outside point charge. So our strategy would be something that is true of a point charge Q would be by superposition be valid for all charges. So let's say this is my point of interest and I draw a sphere around that. Okay, I can orient things such that this charge is on the Z direction. I can choose that, right? And orient my axis such that, okay, this is just a choice that I took the orient such that this is Q and this is my point of interest. Then, so any portion on this surface is our R. This is Z, and this is, of course, capital R. All right, and this is something that you are already familiar with, this configuration. And so this angle is theta. Okay, so so because of that, I can write down what is, okay, this becomes slightly small, Let me see if I can make it, bring it down and sort of resize it. Okay, so resize it to make it larger. Okay, so I'll do that later. Okay, so let me write down the potential V is equal to 1 by 4 pi epsilon naught. That we know here, right? And this is Q by R, is the Griffiths R, because that R. Now here, if you look at the geometry, okay, then this R square is nothing but Z square plus R square minus 2RZ cos theta. We have been doing that quite often, right? So now let's calculate the V average, okay, according to our definition. That is divided by 1 by 4 pi square, the total all potential taken over the whole surface area. All right. So basically it boils down to, okay, having root over Z square plus R square minus 2RZ cos theta, and then dA. dA is of course R square sine theta d theta d phi. We have been doing that also quite often, right? So that is the average, and this integral is very straightforward, and we have been doing that quite often. So Q by 4 pi epsilon naught by, let's say, 1 by 2ZR, and that comes out as plus half, so root. So Z square plus R square minus 2RZ cos theta over 0 to pi. I just plug in the values, then Q by 4 pi epsilon naught, 1 by 2ZR, you just plug in the values and you get Z plus R minus Z minus R. And what is that? Okay, this cancels, 2Z just cancels. There is nothing but 1 by 4 pi epsilon naught Q by Z. Z is this distance. But that's exactly what is this quantity. This quantity is nothing but the potential due to charge Q at the center, at the point. Potential due to Q at R. This was our R position. Okay, we chose that to be the origin, but at some position R. So on taking average, we realized that if Q is here, then if I take the average of the potential, then the potential of this average is the same as the potential because of 1Q. But if this is true of, since it is true of Q, it is true of superposition of any other charges, true of any charge distribution or collection, any charge distribution. So in that sense, it is actually QED proof. So, and you remember that these two are almost equivalent statement. One implies the other. So this is a simple proof. One can prove it in many different ways. There are some problems there. Okay, there's another way which I can prove the same thing. So let's say method 2 for proving. Okay, which is does not directly use Coulomb's law. Here we have used Coulomb's law of potential. Okay, so what we can show, method 2, is we can show what we have defined as V average, show that this idea of if you change the radius V average over, suppose radius R, okay, by dr, then that is equal to 0, which means it does not depend, okay, V average, if it obeys Laplace equation, and V average does not depend on the choice, does not depend, if it is that charge-free region, okay, on the choice of a radius R. How do you show that? Okay, let's start with VAVR, and that is, of course, as we have defined already. Let's first write that down. Okay, this is the definition. This is VR dA, and as usual our dA is R square sine theta d theta d phi. Okay, now so now suppose I want to write down dVAVR by dr. Mathematically, if I am taking this differential inside, I should do a partial integration. I'll take this 1 by 4 pi. This dA and r square I'm cancelling. Okay, so that would become, if I can take del V by del R, this capital R with the radius, right? Del VR sine theta d theta d phi. All I did is this R square and this R square I've cancelled, and in this DAV, since I'm taking inside the integral, I just made a partial. Okay, so now what is that? That is really, I can write down as, since, so this is grad V dot R hat, because in that direction. All right, R hat sine theta d theta d phi. I can rewrite this as reintroduced this R square, okay, but with a purpose. The purpose is that I now say this grad V, then dotted with this whole thing, I put R square sine theta. Now I've reintroduced that. Sine theta d phi. This itself is R. Okay, so what does that give me? Is 4 pi R squared grad V, that was my intention, dot dA. And now I use divergence theorem. Okay, this is this will be del square V dot d tau from here to here. This is over the surface. Okay, this is over the surface and this is over the volume. Okay, so this is grad V, so divergence of grad V. Okay, so this is the key step. But we know that it applies Laplace equation, it obeys Laplace equation, and hence it is equal to 0. So what we have shown that if you do dVAV by dr or variation with AV, then it is 0. It remains the same, and hence since VAVR is independent of rate, is independent of radius R, of radius r, I can say that VAV as r tends to 0 must be V of 0. Simple proof. The crucial application was of divergence theorem here. So this is divergence theorem, and of course fact that del square V was equal to 0. Okay, this is divergence of the grad V, and hence it is Laplacian, and Laplacian is given that Laplacian is 0. So that's proof. So here in this proof we did not invoke specifically Coulomb's law. Okay, we did not invoke specifically so this was just a property of the scalar function if del square V is equal to 0. So it is that stronger in that sense. Okay, so you can take this to be, but the fact remains that there can be there cannot be maxima or minima. That is very crucial. We are going to use in the next. Now let me come to something extremely important. Okay, and let me motivate that. What does it? What are the claims in electrostatics? This is a bunch of things which are called the uniqueness theorems. Uniqueness theorems. Uniqueness theorems in electrostatics. Griffiths does it in some way. We'll follow that. Okay, but in different books, it will be followed differently. So what is uniqueness? That for a properly formulated solution, if there exists a solution, okay, which is properly formulated, meaning it obeys the electrostatics del square V is equal to 0, or del square V is rho by epsilon naught minus rho by epsilon naught, whatever be the case. If there exists a solution, then it is the solution. That is its unique solution. If there is a solution exists, then it is unique. It's a very powerful theorem because, why is it so powerful? Why is it so powerful? Because it assures you, by whatever trick, black magic, or what have you, if you can show that you have a solution which now you plug into the del square V equation and it solves it, then you can be assured that is the unique solution. You don't have to look for another solution. And because of that, many tricks which people have discovered can be used, and then one claims that it is unique. That is the importance of this. So that is the motive. So let's go to what Griffiths calls it as the first uniqueness theorem. We are going to use it in many places, this argument. Okay, the first uniqueness theorem. Let me say it a little more formally. If there exists a solution of del square V is equal to 0 with specified boundary conditions, with which means it is a proper solution. It solves with specified boundary conditions, that it solves the boundary and everywhere in the region. Okay, then the solution is unique. Then the solution is unique. Basically what I stated, but just written little bit more formally. Formally in the sense, it obeys del square V 0, and the solution also is consistent with the specified boundary conditions. The proof is actually, for such a powerful theorem, the proof is almost trivial. Why? Because you just suppose, you negate it by suppose V1 and V2 are different solutions, are different solutions of the same problem, solutions of the same problem. So what does V1 and V2 satisfy? V1 satisfies del square V1 is equal to 0 and V1 and V1 at the boundaries. V1, meaning V1 is not a constant. V1 is the solution. V1 at the boundary. It solves that problem. Okay. Del square V2 is also equal to 0 and solves and specifies the boundary, the same solution. If that is true, then construct a third one, which is the difference between the two solutions, which is, let's say, V2 minus V1. Now, since del square V1, this is a linear relationship, so construct this. So define this. Then, obviously, del square V3 is also equal to 0. It also obeys Laplace equation. But since the same boundary conditions are also followed by both of them, when I'm subtracting it, I'm subtracting the boundary also. Okay, so the boundary conditions now have become 0. Boundary conditions, okay, of V3 are 0. Why? Because the same boundary, they solve the same thing. So Laplace equation is solved and the boundary conditions are become 0. Now, we also know that Laplace equation does not allow for maximum or minimum. Now, in the region, there is no curvature, so it has to be monotonic, and at the boundary, V3 is 0. What does that mean? If there cannot be maximum or minimum and the boundary is 0, implies V3 is exactly 0, which means V1 and V2 cannot be different. V1 must be equal to V2. Proof. Simple and proof, but the result is extremely powerful. So there is actually, this is, though we have said it only for Laplace equation, this can be extended to a corollary claim, okay, to a corollary claim, and it is true. It is, you can see that the proof will go through exactly, even if it is Poisson equation. Del square V is rho by epsilon, okay, and specified boundary conditions. Though, okay, so we are worried about wherever there is rho, we consider that as a sort of boundary, okay, a specified boundary condition. And hence, for any volume, okay, where it is uniquely determined, okay, so let me put it a little bit more formally. Potential in a volume V, let's say volume V, is uniquely determined if a rho is specified, that is charge densities everywhere is specified, and B, the potential is specified on the boundaries. Potential is specified on boundaries. So if you have any volume V, okay, so potential V is specified and all the rho charges, okay, are specified. Rho 1, rho 2, Q1, Q2 or whatever, rho 3, rho 4, and V is specified, then the solution is unique. And that is why these are called uniqueness theorems. Okay, this actually, once this theorem is proved, then it allows for freedom to come up with any solution and show that is a solution. That's it, because uniqueness is already determined by the theorem. Okay, so for example, let's a trivial example Griffiths gives, and it's quite nice. Okay, so let's say an example. Inside a conductor, a region. Inside a conductor, there is a region. Inside a conductor, a given region has no charge. What is inside? Remember, okay? Inside a conductor is given a region has no charge. Then the region is equipotential, meaning it has the same potential as the conductor. Is equipotential, okay? That is the same potential, the same V as the conductor. Now this we have proven that in the last lecture also, but we can here. So suppose there is a this is the and there is a region, let's say, okay, and I'm worried about this region. This is the conductor. This of course E is equal to 0 here. Now the question is that and it has a potential, let's say V naught. Now you can see that if V naught, if this is V naught, then in this region I'm worried about, okay, V naught is one possible solution, is one solution that will satisfy, okay, because it's the boundary is V naught, boundary is V naught, V naught is specified, and del square V is equal to 0, okay. But and V naught, if V naught is one solution, uniqueness tells you that is the solution, and hence that region is charged region inside a conductor, then it is the solution, because I can clearly see that the same potential solves the potential here also. Then I don't have to look for another. It's a trivial example, but shows the power of uniqueness theorems. You don't have to do much arguing in doing so. So I'll take up the second, next I take up the second uniqueness theorem, okay. I'll do that second uniqueness theorem. Let's first understand what this theorem says. Proof is not so important, but the important is understanding. Suppose there is a region, okay, and Griffith says that there are, let's say, conductors which have V1, or Griffith gives it in terms of charge. I don't know how the distribution. Let's then Q1 and then Q2. All these are conductors, okay, with Q3 and Q4 and so on and so forth. All right, the charge densities are known, okay. Then the in a volume V, in a volume, we denote volume V by this according to Griffiths, okay, which is surrounded, let's say surrounded, as I have shown you here, surrounded by conductors. So it is surrounded by conductors, and contains specified rho, then electric field is uniquely determined in the space, uniquely determined if total charge on each conductor is specified. If total Q on each conductor is specified. So it has conductors and it has some charge densities in the space, and on each conductor I specify the Q. Okay, then the E field is uniquely determined. Why is this a important uniqueness theorem on conductors? Because in conductors, I know the charge Q1, Q2, Q3, okay, Q1, Q2, Q3, I do not know a priori how is this Q1 and Q2, Q3 in these conductors are distributed on the surface. But this theorem tells me that there is only one unique way it will get distributed such that the E field is also unique. So if you have a mixture of rho, some charges somewhere, and some conductors, and in conductors at least we know the total charge is specified, then the E field is unique. This is sounds quite easy to understand, but it has both implications, important implications, and it can actually lead to a trap sometimes unless one is careful. I will not directly prove this, but I'll prove something a little bit more general. Okay, so that this particular second uniqueness theorem, which Griffiths calls, is actually becomes a corollary of the. So I consider okay. So let's say I consider objects. Okay, at some. I'm just include also some other results at the same time. Okay, consider objects at some VI in which the objects, meaning let's say conductors, could be I conductors I to 1 to n, okay, and some others, let's say some others have, let's say QI, total charge is specified. For some, so I have a area, okay, and in some it is, let's say, V1, V2, and for some conductors it is, let's say, Q1 and Q2 and so on and so on. Okay, so for some it is Vi and some others it is Qi. Of course, charges will rearrange. Okay, then the E in the space in between, in the space in between these, in the space in between is unique. So the condition is I am given the conductors are with V and Qi distribution. Some of them have been connected to batteries, and in some of them I have isolated charges. Okay, then in the intervening space, okay, my E is unique. So the previous second uniqueness theorem is sort of contained in this, and I will prove it at the same time. A little bit more, the argument can be confusing, but it's easy enough that you can try that. Okay, so of course it must solve the fact that del square V is equal to 0 in the region in between. Okay, and there can be two sets of boundary conditions with boundary conditions. Now, the boundary conditions can be specified basically saying in two ways. Okay, and in mathematical physics, there are names of these boundary conditions. So these are fixed potential, but battery is connected. So fixed potential, let's say on surfaces which are SI. So fixed Vi on SI. This particular boundary condition in quite often is referred to as Dirichlet boundary condition. Okay. Or the other one is that del V dot n, that is del V by n, the surface, basically the surface electric field, if you can say, okay, is specified. Okay, on SI is specified. So either this condition is for an object, either you this specify or you specify this, not both. You cannot do that. Okay, and this is called normally Neumann condition. I don't think Griffiths mentions them, but doesn't matter. It's good to know. Okay, so the two you can choose for different boundary conditions for different bodies, but not both conditions on the same body. All right. If that is that, then the solution is unique. Basically, one can prove that. It's very simple, but let's argue. Okay. So of course, again the same. Okay, construct a V3. Okay, which is V1 minus V2. If two solutions exist, suppose there exist V1 and V2 who are not equal. Okay, such that that is V1 is not equal to V2. That is our assumption, and also that this assumption is not true. Okay, so now let me set up, okay, over the volume V, the divergence, okay, of V3, that is the one that we have defined, V3, and grad of V3 d tau over the volume. Okay, now, but that we know can be shown to be over the volume. This is grad of V3 dot grad of V3 dA. Sorry, I mean not dA, of course, it's d tau. How did I get that? I just used the fact that just a relation. Suppose, let me show that right. Okay, so we know that grad of is a divergence of a scalar function and a vector function. Okay, this is let me create some space here. Okay, so this is f divergence of A. This we have done earlier in the first chapter, plus A dot grad of f. All right. Now look at this. That what? So I now, instead of f, I take grad of v. So f I take v3, and of course A I take grad of v3. Okay. So the first term becomes v3, and this becomes del square v3. Why? Because this is a divergence of a gradient, plus, so this term becomes divergence as a Laplacian of v3, and grad of v3 dot grad of v3. Okay, but we know that this is 0 because it obeys v1 and v2. So it obeys, since v1 obeys Laplace equation, v2 obeys Laplace equation, v3 also obeys Laplace equation. Okay, and if that is true, then this, let's look at this relation. I just, this we obtained from here. All right, but now let's look at the left hand side and right hand side. Okay, so the left hand side, there is this. Okay, I can always write down, let me write down as I, okay, that is over many surfaces. Okay, v3 grad this dot dA. We know this. What did I use? I used the divergence theorem. Okay, so I use divergence theorem here. So if there are many surfaces, then I can, but this, what is this? This is equal to 0, which means the right hand side also should be 0. Okay, so this is 0. Why is it 0? Because either v3 is 0, okay, at the surface, Si. Okay, why? Because v1 minus v2. So, meaning the boundary conditions have been specified, or this condition, either it obeys the Dirichlet boundary condition or is normal boundary condition. So in either case, these two are 0 on the surface. So this is equal to 0. Okay, and hence my RHS. Okay, so let me. So this is my RHS also is 0. But you can see that grad V3 is E3 square. Okay, so it can only be if E3 is 0. So implies, okay, the E3 must be identically 0 for all the integrals, which means, okay, the E1 corresponding to V1 and E2 corresponding to V2 cannot be different, and E is unique. Okay, so the crucial thing that I said, that either this is 0 or this is 0. This is what it depends on. Maybe I should put that in black and white for our, okay. So LHS is 0. I just said that, but let me write it down. Our left hand side is 0, okay, because V3 is equal to 0. That is for fixed Vi. I am calculating on Si. I have already subtracted the boundary. Okay. Or grad V3 is 0. Okay. That is del V by del N have been specified on Si, and it is fixed. And hence, while I'm taking V3, so either of these is 0, and because of that, this is 0. Okay. So, but if this is, there is a possibility that if only delta V3 is 0 on the boundary, okay, then the integral, of course, vanishes. But if del V3 is 0, okay, it means V1 and V2 can at most differ by a constant, and which doesn't really matter. It doesn't bother us in electrostatics and potential if there is a constant also. So one has proved that V1 must be equal to V2, E1 must be equal to E2 for the two conditions, because we got into a contradiction. Okay, so with that, I have sort of proven the uniqueness theorems and talked about in general their power, but we will show their power in the next example that we take up. It is important for us, the proof is not so important. Of course, I'll give you some assignments to be able to use these arguments, but what is important is